Hello, welcome to VLSI design video. In the previous video, we have seen about the floor planning and placement introduction. This is the fourth unit of VLSI design of BE Electronics subject, BE Electronics course. So the second lecture what we are going to see, the objective of this video is to make you to look in detail clock distribution and parameters. So we start with the clocking, why there is a need of clocking or why clocking. Synchronous systems use a clock to keep operations in sequence. For a combinational, do you need clock? No, isn't it? But for synchronous systems and sequential systems, we need a clock. Especially for synchronous, there is a much need of a clock. So distinguish this cycle from this. To distinguish one cycle from the next cycle or the previous cycle, we make use of a clock. And to determine the speed at which the machine operates, the synchronous systems need a clock. So the clock must be distributed to all the sequencing elements like flip-flops and latches. They need the clock. We need to distribute them equally. So these are the sequencer elements which are nothing but the flip-flops and latches. Also distribute clock to other elements. What are the other elements? The other elements are domino circuits and memories. So clocking overhead percentage increases as the frequency is increased. So we need a more need of the clock. So we looking in detail about the clocking. So the clock distribution network is the metal and buffer network that distribute clock to all clocked elements. A clock generator is a circuit that produces a timing signal for use in synchronizing a system's operation. At its most basic level, a clock generator consists of a resonant circuit and an amplifier. The resonant circuit is usually a quartz piezoelectric oscillator or MEMS resonator, although simpler tank circuits and even RC circuits may be used in some cases. Now, what are the primary challenges in clock distribution? It needs to support higher clock frequency based on the strong correlation between frequency and chip performance. Process technology scaling allows higher level of integration and larger die size, leading to higher clock loading and larger distances the clock network need to traverse. So what are the clock distribution metrics now? The main factors which affect the clock distribution are skew, which is called as a clock skew. We need to minimize it. The skew between different clock taps, it is unintentional but we need to minimize. Then the jitter, this also we need to minimize. It is the dynamic variation in the clock arrival times. Next, the power. We need to minimize the power consumption in the distribution network. And the duty cycle. We need to preserve the duty cycle at all clock traps, because we know clock is having unique on time and off time. On time and off time is same. They should not be disturbed. If that is disturbed, that means the duty cycle will be disturbed. And then the triggering of the clock wherever the devices are going to work, that may change. So with that again the skew or the jitter may arise. So we need to preserve the duty cycle at all clock taps. So these are the clock distribution metrics. So let's look into them in detail. Skew is nothing but a phenomenon. Actually we call it generally as a clock skew. It is a phenomenon in synchronous circuits in which clock signal arrives at different components at different times. Getting with me? At different components. Components are again the sequential components or the sequential circuits we are applying, but it arrives to different let me say like for flip-flop at one time and for memory at other time, even though I have applied to both of them at the same time. So a different component at different times. So the clock skew is due to the unbalanced of the data. The clock data what we send, the data what we send, if it is unbalanced, then the arrival times will be different, which results in a clock skew. So this is what you can see. The skew can be positive skew and negative skew. Positive clock skew, you can see here, to the flip-flop 1, the clock has arrived faster, but to the flip-flop 2, the clock has arrived later. So it has taken 3 clock buffer times. It has taken that much time to arrive to flip-flop 2, but to flip-flop 1, it has arrived faster. So FF1 time minus FF time 2 will result in positive, so this we call it as a positive skew. Whereas if you look into the second diagram, the clock which has arrived to the flip-flop 1 is slower than flip-flop 2. So it is taking 2 clock tree buffer time. So it is FF1 minus FF2. Since to the FF2 it has arrived faster, so it results in a negative clock skew. Understood? There are two types of clock skew. One is positive clock skew and the other is negative clock skew. So the time arrival to the different elements or the different components at different times. Here I have shown you both are the flip-flops. It can be, one can be JK, one can be SR, or it may not be flip-flops, it may be something else. But here it has arrived faster. The second element is it has arrived slower. So the first time minus second time will give me the resultant time. The resultant time should be 0 when I subtract, because it should arrive to both the elements at the same time, but it is giving me some positive number, so it shows me a positive skew. Similarly, to the flip-flop 1 it is arriving slower, and to the flip-flop 2 it is arriving faster, so it results in the negative, so it is called as negative skew. Next one is the strategies to remove clock skew. How to remove? If it arrives, how to remove? So we need to locate all clock inputs close together, but it is difficult to implement in a larger circuit. And the other thing what we can do is drive them from the same source and balance the delays. Next is the jitter. It is the cycle time variation of consecutive clock periods. Cycle time variation. See, in one time period, if it is one clock time period is suppose 10 nanoseconds, and the second cycle or the second clock cycle which is arriving is suppose it may say it is 8 nanoseconds. So in the consecutive clock periods, if it is changing, then that we call it as a jitter. So here you can see. So let me say, actually this should be the blue line which is showing should be my ideal clock or the ideal clock edges, what you can see here. But what happens, sometimes it may take this much period, the clock cycle, complete cycle, or it may take here to here. Anytime it can take. The brown lines which are shown here will indicate the variation in the clock cycle. At one cycle it may be the actual clock, the next cycle it may be the variation of this one. So this will result in the change in this variation with the ideal one, which results in the clock jitter. Next is the power dissipation. Clock node consumes more power than any other nodes on the chip. On a microprocessor, clock tree dissipates 40% of total power. So you can see how much it is consuming. So we need to see that this consumption or dissipation should be less. Next metric, moving on to clock distribution. There are 4 basic types of clock distribution networks used in the high performance processor design. That is tree, which is, we can take the example of IBM and Freescale Power PC, HP PA RISC processor PC. So these are implementing tree. Next grid is Spark, Alpha. Examples are next Serpentine is implemented in Pentium 3 and Spine type is implemented in Alpha and Pentium 4. So these are the four basic types of clock distribution networks used in the high performance processors, which I given you with the examples. Each technique has advantage and disadvantage. So you can see here in the table, the grid type, it is having high wire cap, delay is low, skew is ranging between low and medium, whereas tree type, wire cap is low, but delay is high and the skew is less. Serpentine, it is having high wire cap, very high wire cap, high delay and low skew. And the spine type, you can see here, it is having high wire cap, low delay and medium skew. So everyone has its own advantage and disadvantage. These are some of the clock distribution examples I'll show you. First we'll look the grid. This clock grid resembles a mesh with fully connected clock tracks in both dimensions and grid drivers located on all four sides. Usually a custom implementation. It is simple to build, insensitive to load changes and dissipate more power. So this is the regular or the global distribution, and this is again the regular local distribution. And the grid is, as I said, here it is floor, we have planned it, we have all rectangular structures as I told you in the first video. Now the grids here are, you can see like grids. So on the grids my devices or the clock is distributed on these grids. So if I have this block which you see, this block will be now tapping the clock from any of these grids and will use it. Getting with me? So this is one type of connection where we can distribute the clock. Next is the H tree. H tree can be unary and binary. No constraints imposed on buffers and wires. Used mostly by automatic tools in automatic synthesis flows. It can be used for small blocks within a large design. Again you can see this is like a head structure, uniform head structure. The local, global remains the same. You can see here my actual layout or a floor planning, and here you can see the head structure. Like the H, on the H's will be the clock. Here, here, here. So the clock will be distributed in the form of H. So this is not for the placement of the blocks, actual blocks. This is just clock distribution. Next is the spine. It combines grid and binary tree. Put global distribution into spine. Makes it more regular. Local distribution is still custom. So this also looks similar to H, but you can see the real implementation. It is like the spine. So this is the main line for the clock, and from the main clock, it is now, you can see it is taking the spine structure to pass it to the various elements on the floor. Now how to deal with the clock skew and jitter? To minimize skew, balance clock paths using H tree or match tree clock distribution structures. If possible, route data and clock in opposite directions. Eliminates races at the cost of performance. The use of gated clocks to help with dynamic power consumption make jitter worse. Shield clock wires to minimize or eliminate coupling with neighboring signal nets. Use dummy fields to reduce skew by reducing variations in interconnect capacitances due to interlayer dielectric thickness variations. Now be aware of temperature and supply rail variations and their effects on skew and jitter. Power supply noise fundamentally limits the performance of clock networks. Now let's see into the high performance processor clock network. So this is the PLL block, IO PLL. So here is the XX clocks which is generated by the processor. Next it is IO feedback clock. It is 1/4 it is done and fed back. You can see here this is the core PLL from which the clock is generated. It is divided by N and it is divided by 4 and given to IO PLL, or it can be directly given to the core global clock distribution network. Okay, and from the core global clock distribution network, it is passed on to local clock blocks. You can see here these are the LCBs, indicate local clock blocks, to the local clock box or through the IO PLL, IO global clock distribution network, and we can pass, and we have pad clocked elements, core clocked elements. So all this in the basic block diagram I have shown you. So this is the high performance processor clock network. So clock distribution T for a data part. The clock is passed through the buffers. These are the inverters. You can see here. And then to end data path, it is matched with the match delays. This is passed through the data paths. So in this, high peak currents to drive typical clock loads, which is 1/4 of 1000 picofarad. So the I peak is nothing but the current peak. High peak is C dV by dt, and the power dissipation PD is C VDD square F. Now comes the point like from where the clock is generated. So here in this diagram you can see where the clock is generated. The clock is generated using the ring oscillator and the PLL circuitry. So system clock we have already. The system clock positive and negative are passed through the buffers and they are given to the PLL network, and this PLL will generate you the variation of the clock, and it is passed through the synchronizing circuit and given to the various other elements on the platform. So you can see here phase shifted clocks are passed to the XOR. The ring oscillator also is given to a multiplexer, and these are passed through the distributed clock circuit, and then it is given to core uncore primary drivers. So core clock distribution generally happens with the primary driver, repeaters, and simple secondary local clock blocks. It is not with the primary but secondary local clock blocks, and it can be passed either through H's or spines. Thank you for watching.